Good morning, good afternoon, and good evening, depending on what part of the world you're in. Thank you for joining the Elmarco Talks today. Our topic is in regards to ASHRAE 241. And if I can make my presentation work here, that would be great. We have two speakers today, Kathleen Owen from Owen Consulting and John Rajala from AAF International. And before we get started, I'll just introduce myself. I am Tom Burchard, Head of Solutions Management here at Elmarco, and I'm joined by my colleague, Josh.
Yeah, Josh Manasco. Many of you have seen me on previous webinars. I deal with application and business development for Elmarco. Been with Elmarco since 2014. So hello again.
So just briefly, a quick introduction about Elmarco. If you don't know us already, we're the ones that have the nanospider technology. It's an electrospinning technique to produce nanofiber materials. We've been in the market for a little over 20 years. We've got more than 30 patents registered, and globally we have 250 machines installed. That's not only our laboratory scale machines, but also, most importantly, the industrial machines that will be used in air filtration applications. So again, we have a free service electrospinning process. We have a coating head inside the machine that cycles back and forth, coating the wire, the spinning electrode wire with polymer solution, and the nanofibers form from that once you apply the high voltage field. So we have a range of different equipment, all the way from the lab scale to the small industrial, all the way up to the full size industrial. That's the 1.6 meter wide machine you see at the bottom of the screen there. Again, if anyone's interested in more details on that, we'd love to have you connect with us after the presentation and give you some more details on that. A lot of different application areas for nanofibers. The most important one for today is obviously air filtration, and even air filtration encompasses a lot of different specific areas. You have the HVAC, engine air, clean room, gas turbines, dust collectors. Again, today we'll be focused mostly on the HVAC with the ASHRAE 241 standard. So with that, I will hand it over to Josh again to introduce our two speakers today.
Yeah, again, we're talking about ASHRAE 241, and we have two experts here on the standard and in air filtration in general. We got Kathleen Owen. She's from Owen Air Filtration Consulting, which is an air filter cleaner filtration efficiency, and she's a testing expert. She's a member of the ASHRAE 241 committee. She chairs standard 185.5 and is the past chair of both 52.2 and 145. So she has a very good idea of what's going on in the industry and with these standards. And we also have John Rajala. He's the an R&D manager for AAF. He's based out of their Clean Air Center for Global Research and Development in Jeffersonville, Indiana. And in his 7 years with AAF, John has supported development in filtration products, filter media, and application development. He's also the current chair for the TC 2.4 and current chair of the US TAG to ISO TC 142. So with that, I'll let you guys.
And sorry, we have one other point. So Kathleen and John are going to go through their presentation, and then at the end of that, we'll have a question and answer session where you'll be able to type in your questions into the Zoom link, and then we'll have the two presenters answer those questions again after the end of their presentation.
Just make sure to put it in the Q&A part, not the chat for the Zoom.
Thank you, Josh. Okay, so great. We will hand it over here to Kathleen and John. Thank you.
I think that the introduction to me was probably sufficient for this. I am a member of 241. I was also part of the ASHRAE ETF, which was the epidemic task force that put out information during COVID. And I've done air cleaner testing and consulting on the same for, 40 years now. Sadly, it's been a long time. So the talk today is based mostly on air cleaning, but talking about 241 and how we got here and what it does. One of the things I like to say about it is that it tells you how you can use anything to get to where you want to go. That it's the most important thing for me is that we open up how you can do things as opposed to we tell you exactly what to do. But so why did we want to have a 241 standard? Well, the first thing from the ASHRAE perspective and the HVAC community perspective was that we needed to save the epidemic task force information. We spent the first several years of the COVID pandemic trying to get out good information for what people could do to deal with this airborne epidemic from a perspective of air cleaning and trying to prevent transmission through not having the virus get to people. Um, anyway, so that was important because what we found is a lot of us knew from the first SARS that it was airborne. And, you know, we had stuff 20 years old, but we didn't have it in a good way to get it to people. So that was a really important aspect for a lot of us that had been in the ETF. But the other thing is the current ASHRAE standards and other international standards don't actually address pandemic preparedness. We have things for, keeping other contaminants in and keeping temperature and humidity good. So we needed to have this in addition to what we already had. Um, the other thing that was the big pusher and got us actually getting it done and getting it done so fast was the White House asked for it. And just as a note, the epidemic task force information is still up online if you want to look for it at ashrae.org/COVID-19. But hopefully 241 has taken the most important parts of it and improved on it and gotten it out there. So the basic timeline, and just tell you how we got to where we are and why we're still working on the standard. Um, early on with the COVID, we had all the fights with is it airborne or isn't it? And pretty much most of the scientists that at least looked at aerosols and air cleaning believed it was airborne pretty early on, just from the transmission uh, vectors, the ways it got passed around in different locations. But eventually we got to where there were things like the White House seminars and all sorts of different conferences and people recognizing it and somebody finally saying, we need to do something about this. And then the White House contacted ASHRAE and said, we need this. We want it in 6 months. Suddenly it went from egad, some of us would love to do this, but it's going to take us years because standards usually take years, literally, to get through ASHRAE. White House said, can we do it in 6 months? ASHRAE said, we'll do what we can. We formed the committee. We got permission to do it really fast. We got permission to do the standard without the ANSI approval at the front end, which ASHRAE standards usually have ANSI. We're gonna do that later, but we didn't actually start writing the official draft until February 28th, and we sent it out for review in May and sent it out for publication in June. So this is a standard that was put together really fast, but we had literally thousands of volunteer hours doing this. Some folks were working on it, 4 to 10 hours a week on top of their regular jobs. But a lot of work went into it. So it wasn't just that it was short, it was done to the best of our ability. The purpose and scope, and the point of showing this slide, this is actually the words from the document, but the purpose was to look at how to reduce infectious aerosol disease transmission. Looking at how to design the systems, what to look for in your building, and how to add, from our perspective, the air cleaners, and to make sure that what you were getting would reduce the likelihood of transmission. Importantly, the scope does not take away from your standard requirements for indoor air quality for other things, because it is looking at infectious transmission. It's not looking at, do you have too much formaldehyde in the air or too much ozone or PM 2.5. It is looking at pathogens. It's also based on long range transmission, and I'll talk about that a bit more a few slides down. The main topics, and this is in the document, not necessarily evenly distributed in this talk. There are prerequisites and definitions, as one always has. Equivalent clean airflow for infectious risk mitigation is a huge topic that we'll be talking about a good bit. But there's also quite a bit of information in the method about assessing your building, planning, making your plans for what you're supposed to do once somebody decides you're in danger and you need to implement your system. We don't talk about that much in this, but if you are in that side of the the workforce, go to the document. There's all sorts of information there and check sheets and stuff to help you get this done. We're not putting you out there and leaving you on your own. We also talk about air distribution. It talks about air cleaning, and then there's normative and informative appendices in it on a number of topics. The prerequisites. To use this, you have to remember that it only addresses infection risk. I keep saying that, but it's important. You have to comply with your legal codes that you've got for air separate. You can't say 241 said go below the outside air requirements. You have to do your 62.1, 62.2, 170, or whatever else your building is currently required to do. 241 needs to be looked at as an add-on to add additional help. Key definitions, and I've got a slide on each of these, but long-range transmission, infectious aerosol, building readiness plan, infectious risk management mode. IRMM is an important, really big thing for people to get used to the concept of, and then air cleaning and equivalent clean airflow. And then my little graph or figure that I like to show people: when we cough, sneeze, talk, we spit a lot of gunk out. It's in all sizes of different particles. The saliva and stuff that's around your viruses and others, more solid stuff that's in the glops that you put out, it dries down to smaller particles. What we're talking about are those dried down particles that are getting out and about. They're going to other people. This is called long range transmission. You might remember way back with COVID where we had that 6 foot thing. Well, 6 foot is not a magical number, nor any more than 1.5 meters. 6 feet is approximately the distance that somebody can cough and spit and have it glop on you. How far away your kid needs to be sitting on your lap before your face is going to get moist from when they cough. Don't do that at each other. I mean, it's gross to think about, but that's what we're in the business of here, is how do we keep this gross stuff from getting to us? If you're sitting on the plane next to somebody who's sneezing and coughing, 241 is not going to help you. We can't deal with that stuff that goes straight from one mouth to another, or from, that's right there in your breathing zone. What we're talking about is the stuff that gets in the air, stays in the air, and that dilution will help, and air cleaning can get rid of the stuff before it gets to the next person. So important to remember that if you think you've got a sick person, don't sit next to them, send them home. But use this if you want to try to keep from getting the whole room or the whole building infected. This slide, infectious aerosol, is just an airborne particle that's infectious, that's got viruses or bacteria in it. And the graphics are just to show you that you can have all sorts of different sizes of particles coming from different speaking, coughing, and anything else that you do that causes it to come out of your body. Building readiness plan, another, just hitting on this because it's an important part of it. In addition to your normal documentation for your building, there's specifications called out for things you need to check on. And in this case, a lot of it is your air cleaners and make sure your airflow is right. The biggest thing people have found in looking at this is that if they need to get their basic plan followed that they started with. And that's critical. But this is additional information you should collect and have ready for your building. IRMM, infection risk management mode. This is the point in time where someone decides that you need to go into protect yourself from a pathogen mode. It could be your governor declaring that the whole state needs to go into this. It could be your business owner. It could be somebody that says, hey, the last 3 months, we got such good results at being in our IRMM mode that nobody was out with the flu. Let's stay that way. But whatever it is, someone, not 241, has proclaimed that you need to go into IRMM mode and start running your protection. Air cleaning, pretty basic for most of the people who would be on this talk. Air cleaning in the sense of this method is anything that reduces infectious aerosol concentration through capture and removal or inactivation. Either get it out of the air or make it so that it can't make you infectious. So one of the things you have to remember, like if you use UV, the stuff may still be in the air, but if you breathe it in, it's not going to multiply in your body. it's safe from the perspective of getting sick. And a big note from ASHRAE, please, we don't specify technologies as being the right one to use for 241. We mention the technologies that are best understood because it's easier to call them out for how to put them in the equations. But we don't say anybody's better than anybody else. We say get good data and use it. We're very data driven. But air cleaning technologies include mechanical filters, which I tend to calling media filters, UV and reactive species. And if there's something that's not in that list, it could include it too. Equivalent clean airflow. Equivalent clean airflow is the rate of pathogen-free air that, if distributed uniformly within the breathing zone, would have the same effect on infectious aerosol concentration as the sum of, etc. You can read. It basically is the amount of air that the risk assessment people that put 241 together determined was needed per person to do the risk reduction at the level that 241 decided was the level to go to. We're not 100% gone, we're reducing significantly, but it is a per person amount of equivalent clean air. And equivalent clean air includes anything that's reduced in infection. So outdoor air is considered clean air for the perspective of human generated aerosols. If you happen to be pulling outdoor air in from your sick porch where all the people are sitting outside coughing, don't do that. But basically, your clean air can be outdoor or it can be air that's been cleaned inside the building. If you clean incoming outdoor air, you don't get extra credit for cleaning clean stuff. It is a mathematical construct. For example, if you have 100 CFM of pathogen containing air, the air coming from your room with a person that's, infected in it, and you run it through a 50% filter, you get 50 CFM of equivalent clean air. This does not mean that you have 50 CFM of clean air and 50 CFM of dirty air. There's still 100 CFM of mixed air. But for the math of it, that's considered to be 50 CFM of clean air. Outdoor air, again, is considered clean, so 100 CFM of outdoor air is 100 CFM ECA. That's my definition of ECA. The BRP, again, is the building preparedness plan. And one of the things that you do when you apply this is you figure out how much air you're already getting. How much are you meeting your ECA goals already? How much more do you need? And again, checklists and guidance are in the various appendices. And as I just said, because I forgot the slide was coming, when you go through your assessment, you look at your target, you figure out what you're getting, you figure out what you need more. You may find out you don't need more. And then you plan for what you want to do to get to the goal at the time where you need it. And you can even have more than one plan. You could have a summer plan for, in North Carolina, it's hot. You shut the windows and you put in more air cleaners. But in the fall, you might want to open the window. You can do it more than one way. There is information on maintenance to add to your basic maintenance plan, but if you're using in-room air cleaners, you need to keep an eye on them, make sure they're working. UV lamps may need to be changed. Basically there's some additional work you have to do in addition to what you would normally be doing. Add that to your plan. We also have additional requirements for dwelling units. The reason this is important is in your own home, you're somewhat more likely to know which individual is sick. If somebody's got a COVID test, you want to keep them in the bedroom. You want to put the air cleaner near them. You do what you can to keep them from spreading it, but you've also got more control because you can set up a bedroom separately. You can set up an individual room. You can have you can keep children away. The other thing is to remember that if you flush a toilet and somebody has deposited things that have viruses in them, you can aerosolize stuff. Keep your lids on year round. So, and that's gross again, because viruses are gross, but it is something you're much more likely to be able to have control in your home. So that's something we talked about. Okay, so moving on to how do you figure out what this ECA is? It's a magical number. Not really. There's tables for it, but your ECA is your amount per person. You multiply it by the expected occupancy to get your V sub ECA. So that's your like volumetric airflow rate, your total amount of air that you need. There's different categories, 25 different space types, and I think we're working on more. But you go and you look up the category you think that you fit into. You figure out from your building assessment what you need. You multiply two numbers together, easy. Here's the table. If you have a correctional facility cell, you are looking at 30 CFM per person. It's fairly straightforward. If you have a space with loud vocalization, this was intended to be things originally we were thinking of church spaces with loud singing. But we found some places, you have church services that aren't loud, but you also have business meetings where they have a speaker that gets you to stand up and yell. You know, if you're doing that type of stuff, double this, because you're giving off, your sick people would be giving off a lot more virions. I think I went backwards. Comparing ASHRAE standards and CDC, one of the big questions that we get is, why does ASHRAE say something different from CDC? And what difference does it make? So I've given you the go look up CDC if you want to, but basically CDC was saying go with 5 air changes per hour. ASHRAE is doing the how much per person. These two, this slide and the next one, are just to show you that if you look at it from a CFM per person rate, the different methods do give you very different answers for different types of spaces. In some cases, you will save a lot in how much you need to produce. In some places, it's more. But it is a big difference in terms of the perspective. For example, if you're looking at CFM per person, ASHRAE is looking at having more air per person, whereas the CDC, it's the same amount per person. Likewise, if you look at it from the air changes per hour, the 241 is much higher in air changes per hour for some, and CDC is for others. To meet the VECA target, remember that's the total clean air, equivalent clean air airflow that you need. You've got the outdoor air, that's the natural ventilation. And then you've got all sorts of different places you can put an air cleaning system. And there's different equations in there for how to do it. But if you have an air cleaner that's in the room, you figure out how much is added to the room. That's easy. If you have it that's split, for example, some of your return air is venting to the outside and some is going through the air cleaner and back to the space, you only get to take credit for the amount that's coming back to your place where there's people. But since you can do this, you can put a MERV 13 in your system or a MERV 9 if you want to, but some of them you get credit for and some you don't. But if you can't get it from your HVAC, if you can't get it from your outdoor air, you can add in room. Think of it as being credit for most things that you can do. One big thing to note, and John might talk about this a bit more later, is if you're using a 52.2 test result or a MERV, you're going to have to get the MERV A, which is with the optional Appendix J, to use to count for your credit starting January 1st. Equivalent air, clean airflow for a filter. This is just an example looking at it, the simplest note. If you've got air going, return air, recirculated air going from your breathing zone into an air filter and coming back to the space, you multiply that amount of air times your efficiency, and assuming your efficiency is in percentage, you divide by 100. That gives you your VACS. Very straightforward. This slide is included not so that you can read all of it or worry about it too much, but to remind people that you can have a very different influence on your cost depending on your climate zone. And this is where I say to people, think about this, but remember that you're trying to keep people from dying or not being able to come to work and your company going under. That's your goal if you're in a pandemic. It's not long-term. But also, if you've got that seasonal difference, use it to your advantage. If you've got a pandemic that hits in nice weather and you've got openable windows, use that to the extent rational. because you don't want to kill yourself off with the energy. But so when you're planning, think about all the different ways you can use this to keep you healthy and not to kill your budget or use too much energy. You have different ways you can meet the goals. And I'm going to pass over to John to talk to you about air cleaning and effectiveness and all that. I will be back.
So just gonna pick off where Kathleen left off and go through some other stuff. Also, thanks for the nice intro earlier, Josh. I think you covered my credentials fairly well. The main thing, as Kathleen was pointing out, the driver of this standard was the lack of information and standards related to air cleaning systems, which was a big problem during the COVID pandemic. When we talk about this safety and effectiveness, we discuss effectiveness. It's how effective, the ability to remove or inactivate infectious aerosols, the air cleaning system is. Again, this standard is not talking about removing anything other than the infectious aerosol. So we're not really talking about PM control or anything else, gas phase species or whatever. It's just particular to these infectious aerosols. When we talk about safety, you have to consider with these air cleaning systems, there's other adverse effects that can be related to, such as direct exposure. You don't want to be exposed to UVC. It's effective at inactivating infectious aerosol, but it's bad for your skin and other effects like that, as well as oxidants in some of the air cleaning systems. They can put out some bad stuff that you don't want to breathe in. So you have to make sure that some of these air cleaning systems are vetted for those safeness of use. And then secondary contaminants, if there's any kind of particulates or ozone or other kind of things that are being generated from an air cleaning system. And Standard 241 establishes the minimum requirements for these effectiveness and safety testing. So when we go into this testing, again, Kathleen pointed out earlier, Standard 241 does not recommend or rank technology. So it's not saying, filters are better than UV or UV is better or, other air cleaning devices. It's just meant to compare what works and how to operate a building in a way that will reduce risk of infectious aerosols. And it does establish a level playing field for enable use of effective and safe technologies. So again, if you want to use several different mechanisms for reaching these levels, it establishes what you need to do to get it done. So you can use a combination of different, technologies or, whatever works best for operating our building. The methods of tests that are referenced, such as ASHRAE 52.2 for filter testing, ASHRAE 185 for DUV light inactivation, AHEM AC1 and AC5 are for different air cleaning technologies, and ISO 6890 is another filter test that's more prevalent outside of the US. And normative Appendix A provides you the procedures and the guidelines to how to determine the effectiveness and safety of these devices when a standard is not available. So when we talk about the filter specifically, Kathleen pointed on this just a little bit, but when we were talking about filters, which is more my expertise and specialty, I wasn't part of 241 developing this. I've kind of followed it and tracked it. I'm the current chair of TC24, which helps provide some guidance on the particulate contaminant side of what's going on at ASHRAE. But when you look at this table, it kind of provides an equivalency between the MERV ratings and the ISO 6890 ratings. Anything less than MERV 11, which has no minimum requirement for the E1 E1 particles in the ASHRAE 52.2 standard. So those particles less than 1 micron, you get no credit for infectious aerosol removal. And then as you increase the MERV rating, MERV 11, you get credit for cleaning 60% of infectious aerosols through that filter. And then, 71% for MERV 12, 77% for MERV 13, et cetera. That's, a way of, as Kathleen pointed out, you can, it's not saying that, you have X CFM of clean air, it's a way of kind of saying the effectiveness on how many of these infectious aerosols you'll catch and cleaning the air, making it more safe to occupy. But when you look at this table, you see that after January 1st, the MERV ratings will be using the Appendix J MERV A ratings. So I put some slides in here on top of what Kathleen already had. When we compare these test standards, I guess 3 main prevalent test standards globally would be the ASHRAE 52.2, the ISO 6890, and then the EN 779, which was what was used in Europe prior to ISO 6890's development. And after 6890 came out, it kind of made that defunct, and it's not used as much anymore, except people may be referencing the old filter efficiency classes based on comfortability and knowing what they were. I hear a lot of people say F7, M6, that kind of thing still. But the main difference between 52.2 and 6890 is that conditioning step that I highlighted in the red box in the middle of the screen. Optional and 52.2 is Appendix J. If you look below, conditioning substances, sodium or potassium chloride, KCl particles, and you're measuring, basically you're bombarding the filter with lots of small salt particles, and it decreases the filter efficiency over time. And then once that drop stops, being significant, then it ends, and you can document what that minimum MERV rating is. But again, it's an optional test; it's not mandatory, and frankly, it's not very widely used at this time. ISO 6890 is an IPA vapor test where you can basically test the filter's efficiency, put it in a box with IPA vapor, let it sit for 24 hours, take it out and retest it. It does a good job at stripping that electrostatic charge off the filter, and it measures kind of the worst case minimum efficiency of the filter based on that charge being gone. When you do the 52.2 test, you run several efficiencies, and whatever the worst case is, the lowest efficiency throughout the procedure is what's reported as the 52.2 MERV rating. The ISO 6890, they take that initial charge filter and then that discharge filter condition and average to find out what that minimum efficiency is. So I put in some test reports on the next couple slides to show you what this means. So when people talk about 52.2, when you look at a 52.2 test report, this is most likely what people will see. A lot of filter companies or filter users will use just an initial efficiency test. So they'll run one efficiency and they'll say, okay, this is a MERV 13 filter. So I highlighted out the arrow's pointing right at that E1 efficiency, 63%. So it's removing 63% of particles at that size range between 0.3 and 1 micron. And you need to be above 50% to get a MERV 13 rating. But is 52.2 really a worst case scenario? Well, if people are using this isn't the full 52.2 test. So if they're reporting this as their MERV rating, it's not the worst case scenario. It's just the initial efficiency. If you run the actual 52.2 test, it would look something like this. We are running several dust loading steps and then testing the efficiency after each dust load step. Now, on most filters that don't have electrostatic charge, the efficiency will just increase over time because you're building a dust cake layer and making the filter more efficient over time. But it's on some of these electrostatic filters, you can drop efficiency a little bit, and you'll see, in this case, this is basically the same filter that the previous test report was for, but that E1 percentage dropped from 63 down to 40, and that takes it down to a MERV 12 rating. So when you look at this, you can see, that if you just report the initial efficiency, you're not always reporting the worst case scenario of the 52.2. But is this really the worst case scenario? No, because if you run an Appendix J test, this is similar filter, not exactly the same, but same concept where it starts at a MERV 13. Sorry, my text got a little funny there. But I want to point out start was MERV 13. It started at that E1 range of 68.4, but with the Appendix J conditioning, that E1 range dropped all the way down to 21%. And the E2 dropped pretty significantly too, from 92 to 53. So this MERV 13 filter with an Appendix J test dropped all the way down to MERV 10. So this is the kind of thing you're seeing in the market on these kind of MERV 13 filters. And the point of using the Appendix J testing in the 241 standard would be kind of showing more of a true efficiency of what the filter would look like, as opposed to kind of masking that the minimum efficiency behind the actual 52.2 test right now. When you look at the ISO 16890, they made this mandatory. So you can see here that bottom line is the initial efficiency. So this is a similar efficiency filter as the one that I was pointing out in the other test report slides. But you can see here, actually the bottom one is the average. So the initial is not shown on this test report. So it's that top curve is the average, the initial efficiency. And then when you condition with IPA, it dropped down to that top line. And then the PM1 ended up lower than 40% on the minimum. So you take the rating from the minimum efficiency that's above 50%, which is in 2.5, and then you can report it as the average, which is above 70%. So this filter would be an ISO EPM 2.5 70% filter. So with this ISO test, you can see it's an easy way of showing what the initial efficiency is, what the minimum efficiency is, and how the average gets reported. And this is more like a realistic view of how the filter might be over its life. And then when you look at, since we're talking about with Elmarco and some nanofiber stuff, I put in this slide to show some of these comparisons. So if you take a MERV7 filter that we were looking at, during COVID, and add some nanofibers to it, you could boost that same filter to a MERV11 by adding nanofibers. But of course, you double the initial pressure drop of the filter. But if you take that same, take a MERV11 filter that's with electret media, you kind of, the pressure drop's kind of in between, that's 0.3 compared to like a 0.2 and a 0.4. But we know that MERV11 will drop down to maybe a MERV9 or MERV8. So, using nanofibers is a good way to try to help bridge that gap, and it won't drop with the Appendix J testing. So it's not an electrostatic charge filter by any means. So get back into the 241 discussion more specifically. So the way these air cleaning systems are classified in 241 are in-duct air cleaning systems, which clean the AHU duct or plenum. This would be like your filters or UV systems installed in duct. And then you've got systems that clean the air in occupied spaces, systems that clean the air in occupied zones, and then mechanical fibrous air cleaning systems. As Kathleen mentioned earlier, this is more called media filters in our world. When sometimes the filter people use mechanical to mean non-electrostatic charged filter media. But everything's considered mechanical in terms of the standard because it's physically, mechanically removing something from the airstream. And then systems that inactivate infectious aerosols would be like your UV light systems. So we look at the AHEM AC1 test. This is for kind of in-room air cleaners. They use a clean air delivery rate for smoke, dust, and pollen for the different size ranges. So the way 241 handles this is they kind of weight the average between the efficiency of smoke, dust, and pollen so that you can, get a quantification of how the system works at different particle size ranges. So just like the 52.2 standard table was broken down by, I think, the same kind of percentages, 30, 30, 40, on how you weighted the particle removal by size. Again, you can do the same way and apply them to these in-room air cleaners tested by the AHEM standard. And then we talk about systems that inactivate infectious aerosols like UV light. The effectiveness is, quantified by the ASHRAE standard 185.1 using MS2 as a challenge infectious aerosol. And then the safety of operating systems is in that Appendix A, as pointed out earlier. And for the induct systems for removing infectious aerosols, there was an Appendix L added to the 52.2 standard. It's out for publication now. Review to look at adding this officially to the standard, but it was added as like an addendum on the ASHRAE website currently. But it's basically taking this 185 standard and applying it to induct systems that aren't UV light, basically. And then running down some of the Appendix A requirements to 241. The standards, you use the consensus standards, as we mentioned before. So for filters, 52.2 and ISO 6890, for UV light, 185, etc. Or custom protocols if they're not available. So, we just need to find a way to effectively test these and make sure that they're used appropriately. For parity, you want to have the same conditions for effectiveness and safety tests from lab to lab. So the laboratory, we want to be compliant with the requirements of ISO, IEC 17025 or equivalent, to make sure that the lab is doing things properly as well. For these chamber tests, you want a minimum to be 800 cubic feet so that you can appropriately test from device to device and be the same. For test ducts and duct systems, follow what's in the standard. And the test microorganism is MS2 for testing the organisms. So effectiveness in the testing requirements, you got to take into account natural decay. So you have to run replicates with the systems on and off so that you can determine how effective the system is, and not just running it with it on and not having that baseline comparing, a condition where it's not. So when you look at these charts, you can see with the air cleaner on, obviously it'll clean the room much faster, but these particles do settle and decay over time. They get stuck on the walls, drop to the floor, that kind of thing. So you use, it's in the AHAM standard where you, effectively test with it on and off to measure how much more effective it is than the natural state when you're applying these standards. And then for safety testing requirements, chemicals, noise, UV light, combustion byproducts, and manufacturer certifications. These are all in here as, what the appropriate restrictions on these contaminants are in a space. So there's, regulations out there on how much ozone or formaldehyde or whatnot are supposed to be in a space. And then you want to make sure that you're going to be operating safely so that these devices or whatever you're doing to the system is not going to produce more or operate in a system that has excess of these harmful contaminants. And then there's also a calculator that ASHRAE developed, the committee, 241 committee developed, where you can download it and use the tool to type in conditions in a space, and it'll tell you if it fails or passes the equivalent clean air ECA as classified by the space. So again, you can put in a classroom. It pulls in all the information from what your target ECA is, and that's CFM per person. And you can put in how much outdoor air, what kind of filters you're using, whether or not you're using UV, how effective it is, etc. And then it'll kind of calculate what that ECA is per person, and then it'll tell you whether or not it meets the requirement that you're looking for. So again, that first column, it shows 14.8 CFM per person. That's below the 40 required. So then you can look at the other options to see what you can do to adjust that, by reducing occupancy in the space or adding filters or bringing in more outdoor air, that kind of thing. And as Kathleen mentioned, there's going to be, it's a standard now, so it's going to be under continuous maintenance. We're going to be working on it. Obviously, getting that ANSI certification will help, get the process more formalized in how they update and document the procedure moving forward. So there's going to be a lot of publications, presentations, and a web page to communicate this, and then testing with buildings to see how this works, and then hopefully get certified down the road, and then referencing the standard and other ASHRAE standards so that it gets more legitimized and formalized in the procedures in ASHRAE or the standards. And then eventually maybe this will get adopted into codes, and people will be specifying this document and looking to target it for what they're doing moving forward. And then as continuous maintenance, there's FAQs and energy use requirements and more space types. So again, I think the committee knew it wasn't going to be a perfect standard being created in less than 6 months, but we need to keep working to make it better. So with that, that's the end of the presentation. So thanks for giving us the time to talk about this.
Great. Thank you so much, John and Kathleen. So we'll open it up to questions, and I think we've got one here in the from the Elmarco side of things. Can you guys comment on where people can obtain the 241 standard?
The easiest way, if you're cheap like I am, is to go into the ASHRAE standards free read online, and you can read it. You can't download it, or you can buy it from ASHRAE. And I recommend, as always, use your search engine, but not the ASHRAE one to find it. So ASHRAE standard 241, and either look for, you know, free or buy, and you'll get to it.
Okay, great. Thank you. And what about John, you were showing some of the resources on the sort of like the Excel spreadsheet. Where is that available?
The link wasn't on that page. I don't remember what it is, but it's on the slide.
Okay, great.
Again, though, it's also, if you Google equivalent clean air calculator, I think it is, you'll get to it.
Yeah, ashrae.org/241-2023. So I
Thank
think
you.
the 241 standard has a web page that you can look at the information for and download this calculator. So again, if you
I
just
believe
Googled
if you
ASHRAE
buy it,
241,
it heads you to it anyway, but you can get it separately.
yeah.
Great. We will share that with all the participants. Thank you. Josh, do you
Yeah,
have one?
so back to talking about the filter testing and the MERV and the ISO rating. Is it that when you have an ISO 16890 rated EPM filter, that it gets credit for the same MERV A filter level that was on the equivalency of the chart?
Correct.
You had a chart with MERV and ISO.
Yes.
Yeah. Whichever rating you have, go to that table and pull the efficiency.
Right, so that table you have MERV 11 through 16, and then you have HEPA, and then you had an equivalent EPM 2.5 or EPM 1
Right.
there. So that just means that whenever you have if you bring a filter from Europe into into the US, and we're looking at 241, that you would get the credit for EPM 1, 50% would be the equivalent of a MERV 13A. Is that right?
Well,
Yes.
I think that, yeah, in essence, but the basic goal is that you would use that 77% number.
Yes.
We weren't able to, in 241, to say that the MERV and the ISO 16890 are exactly the same thing. So I don't want people to be going out and using this table to say, oh, an EPM 150% is exactly the same as a MERV 13. But it is true that you get the same weighted efficiency credit in 241.
Yeah, with the
So
ASHRAE
if you
52.
Oh, go ahead, John.
Sorry. With the ASHRAE 52.2 standard, there's just the 16 MERV ratings, but with the ISO 16890 EPM ratings, there's something like 70 something different filter ratings that you can have, because it goes by 5% increments on the EPM 1, 2.5, and 10 and course ratings. So there's a lot of different combinations. I think they're even looking in that committee to reduce the number of ratings you can have by cutting it to 10% increments instead of 5. Eventually down the road, maybe.
But basically, if you've got your filter with a 52.2 test as of January with the Appendix J, but right now just the MERV, or a 16890, or an MS2 test, any of those things can be used to give you the efficiency to plug into your calculations.
And could you explain again what MS2 test is?
The various ways of doing the inactivation testing. MS2 is the surrogate, the virus surrogate that's used, that's chosen by 241, and a lot of the labs are using it to give you an inactivation efficiency. The thing is, if the stuff is removed from the air, it's going to show as not being active in the air anymore. So you can do it. But the basic thing is, any way you got your filter tested, that's a standardized test, you can use the efficiency from one of these, either the table or your test report. And one of the fun things is, somebody pointed out to me the other day that if you've got a MERV 11 and you have the inactivation test, the MS2 test, you can get credit for the MS2 test, even if you can't use the 52.2. I don't know that we intended that, but it's the way it's written.
Very interesting. I just want to let all the participants know that if you have any additional questions, again, obviously we're asking them as we see them, but you have to go to the Q&A window in the Zoom meeting to send in your questions. Don't use the chat window. So with that, I'll let Josh ask one of the other questions we've got.
Yeah, I've got a very loaded question. I think that at least what I've heard is that 52.2 is sort of trying to harmonize a little bit with ISO 16890, like in the past, or it's like there's been discussions about it. Do you ever see? We're very interested selfishly because we make nanofibers. Our equipment makes nanofibers. So thank you, John, for mentioning that in your discussion. But we're interested in the media and mechanical side of the media, of course. Just thinking about what your opinions would be about Appendix J becoming more like a mandatory standard in the future for 52.2, or is that completely out of the question?
Okay, as the past chair, where it came up a number of times, and part of the project team that developed Appendix J back in the day, it has come up for discussion at least every 3 years because it's been, I think, a part of 52.2 for 15 years. It might even be 20 by now. We have never been able to get more than 50% of the current voting members to want to move it in. We have some of us that are adamant that 52.2 needs it or it's going to die, and we have some that say it's not good, that there's no point in doing it. I don't see it happening, but I do see more people going to 16890.
I
I
would,
don't, one of the questions while I was chair, so like 4 years ago, that ASHRAE asked us to look at is, did we want to sunset 52.2 and have the ASHRAE standard be ISO 16890? So there are a number of different ways that filter testing requirements can change. And as somebody likes to point out to me, back in the the dawn of creation, or like the 1990s, we didn't have 52.2. So it's not that 52.2 has to stick around forever, but right now it looks like it's going to stay Appendix J optional.
yeah, I would tend to agree with Kathleen that the slower 52 is to act on adopting Appendix J mandatory or something similar. 16890 is probably going to start, infiltrating in the U.S. And be more prevalent if people are asking these questions. But also, quite frankly, the 52.2 Appendix J test sometimes can take multiple days to run because sometimes those heavily charged filters will lose efficiency fairly slowly. And depending on how much conditioning aerosol you can generate, it could take up to a week to run a test. Where the ISO 16890 Appendix J IPA vapor conditioning, you just put it in a box for 24 hours to take it out and run a test again. So it's a lot less active using testing on that. So if test labs seem to think it's more easy to run an IPA vapor conditioning, they might just do that anyway. And then you'll start seeing those test reports come into the market, and then it might just kind of supersede Appendix J anyway.
Of course, on the Appendix J side, if it were to become mandatory, the labs would get faster at it because they'd buy more nozzles and they'd do it more often, and they would get it automated to run overnight.
Yeah.
But given the push in other standards and other locations too, like 170 and 62, to get that minimum, the realistic discharge or masked efficiency value to use, so something that's lower than the MERV for a charged filter. I think there's going to be other places that are pushing, not just 241. So we'll see. It'll be interesting, and I'm glad that Todd is the chair of 52.2 now.
Yeah, and you can feel free to join us at a 52.2 meeting to be part of this fun conversation.
Yes, anybody here is welcome to join. ASHRAE does have public access meetings.
So we have time for like one or two final questions, and we have one from another one from the audience. Why did ASHRAE decide to use the potassium chloride, the KCl particles, instead of IPA vapor?
Okay. The research project that led to Appendix J asked us to develop something that imitated reality. So the RTI project team ran real filters in real buildings and looked at how far they dropped. And we tried to develop something that was based on something that filters could be exposed to, like particles, that would do that. And we tried a bunch of different types of aerosols, including diesel exhaust and things of that sort, and found the 40 to 50 nanometer particles that like coat the fibers, dropped the efficiency, usually about half of the total distance it could go when you used what we consider to be equivalent to about a 3-month increment of exposure. And so that was where the Appendix J came from. IPA came about as a concept, at least that I heard of, somewhat later, because originally we were actually dunking the filters or pouring the IPA on them, and it was dissolving the cardboard, and the glues. So yeah, the thing is, we're talking that we developed the Appendix J like 20 years ago. So but it was intended to be something that didn't drop the charge the whole way, but dropped it about the amount that you would see. Admittedly, for filters that were on the market that many years ago. So I can't say that it would be realistic with all filters today.
Sure.
But
okay, great.
and a lot of people, when IPA first came out, were saying nobody's got that much IPA. Nobody's exposing their filters to alcohol. So it's taken a while to get people to accept that that's an acceptable test method.
Right. Great. Thank you so much. Again, I know we could go on for at least another hour answering everyone's questions, including my own. But we have to wrap it up here. Really want to thank our two presenters, Kathleen and John. Thank you so much. Round of applause for you guys. And thank you to all of the participants. If you have additional questions, feel free to send those into Elmarco. We'll certainly work on addressing those with our two presenters. And again, and the presentation will be posted in the next few weeks. So again, thank you so much to everyone. Appreciate your time today, and we will see you next season starting in the fall.
Thank you for having
Thank
us.
you.
Thank you, everyone. Have a good day.
Yep.
Thank you.